Okay, Bismillah ar-Rahman ar-Rahim. Welcome back to the lecture. This lecture, ya shabab, we are going to talk about two sections. They are very much close to each other, very much related to each other, and it is going to be very nice to, cover them in the same lecture. And basically, we are going to talk about frictional contact axial clutch, and then we will talk about cone clutches and brakes. They are very, very similar to each other. So to start with the first one, which is section 16.5, and then we'll skip section 16.6 because it is a reading assignment, and then we will discuss section 16.17. Sorry, section 16.7. So as for the frictional contact axial clutches, an axial clutch, as defined here in the slide, is one in which the mating frictional members are moved in a direction which is parallel to the shaft direction. So basically, in this way, we have one frictional side and then the other one. And then if this is the shaft and the two discs are parallel to each other, you have to push one against the other in the same axial direction. And that's how they get engaged. And then the motion is basically transferred. And if you look here, this is an example of, for example, a material over here. Let me just, sorry. It's, if you look at it over there, you can imagine that this is like a disc, and these are like two pads. And if they basically are being pushed, they will get engaged within the motion of the disc itself. Okay. Now, we have usually in such problems, we are mostly interested in determining the force necessary to produce a certain torque and to maintain or reach, or let's say attain a certain pressure. So you want to know how much should you push in order for you to achieve a certain torque. And at a given pressure. Usually, you can predict that in the coming slides that we are not going to talk about pressure in general. We are actually going to talk about PA, which is, we said that this is the maximum pressure that the frictional material can withstand. So what you are going to see next is basically a formulation, okay, of what is that force that we need in order to reach that pressure, and what is the associated torque for that. Okay, so that's what you are going to see. Of course, ya shabab, we are not going to go over the integration and the derivation of this, but you can imagine here in a simple mathematical form that we have an annulus disk. This is an annulus disk. And this disk, okay, we can imagine that there is a strip, okay, dr, surrounding this annulus. And basically, we are going to analyze the strip and integrate over from the inner diameter or the inner radius all the way to the outer radius. Is that right? This is what you should imagine. So you can go and see the derivation in details in the book. Even when I include here the integration as a form, I am not going to discuss it into too much details. Now, but before we start, I want you to focus with me on a very, very important concept here. This slide, you need to read it very, very carefully. It will make the remaining part of this section, 16.5, and section 16.7 very, very easy. So please focus with me over here. There are two methods for solving the problem. Which is the problem? Determining what is the force required to reach a maximum pressure and what is the associated torque with it. Depending upon the construction of the clutch, In general, we have two two approaches. In the first one, we said that the disk is rigid, okay? Or the disk, if there are multiple disks, they are rigid. And then what happened? The greatest amount of wear will at first occur in the outer areas of the disk. Why? Because as the angular velocity is the same, but we know that the linear velocity will change, and it will be maximum on the top, at the most outer layer. That's why the outer layer is going to wear more than other layers. So what happened? Since the work of a friction is greater on those areas, which are the top layers, after a certain amount of wear, which has been taken, out, the pressure distribution will change. So as to permit that the wear become uniform. So what happened? If it is too rigid, it means it will not deform. And there is wear happening more on the outer surface because of the speed and whatever, then the pressure has to adjust in order to make the wear uniform. And this is the basis of the first method. So you can imagine that in the basis of the first method, we have what a we have a uniform wear problem. It is more like a uniform wear problem in which the pressure has to change in order to maintain that uniformity of the wear. Okay. In the other one, in the other method, it is usually constructed by employing springs, and these springs will adjust the mechanism such that the pressure will always be uniform. So we have more like a uniform pressure problem, a uniform wear problem. Okay? Now, so these are the two problems. Now, this is not the end. Probably you understood now that there is a uniform pressure problem, there is a uniform wear problem. There is one little bit here that you need to understand. If you understand it well, things will become very easy.